Alright, welcome back to Meteorology101.com. In this video, I'm going to talk about humidity, condensation, and clouds. So visit our website at Meteorology101.com and get your head in the clouds. Alright, water circulation in the atmosphere. And I did a video on the layers of the atmosphere, so if you missed that one, go back, watch it. Talk about different layers of the atmosphere. Our layer of the atmosphere is the troposphere. And the water vapor in our layer of the atmosphere, which we live in, is only 0 to 4% of the air and is responsible for most of the phenomena we call weather. Clouds, precipitation, dew, frost, fog. So we say most because wind is weather. There's a lot more to do with weather than just precipitation. So 4% of the air contains moisture, water vapor, and causes most of our weather. So the water circulation of the atmosphere. The constant circulation of the water through the Earth atmosphere system is called the hydrologic cycle. We'll have a graphic on that here shortly. Simplest form, water cycles from the ocean to the atmosphere by evaporation, from the atmosphere to the earth by precipitation, and then back to the oceans, just a runoff of the land, or just rains right back into the ocean. Oceans are the driving force since the earth is about 70% water. During the hydrologic cycle, lots of things can happen to the water during this cycle. So evaporation, condensation, precipitation, transpiration. So evaporation, the oceans evaporate, that water vapor goes into the air, condensates onto dust particles, salt, any particle that's in the air, could be smoke, pretty much any particle, and creates clouds. Condensates onto a particle, becomes a water droplet. The water droplets collide, coalesce, become bigger water droplets, and then you'll actually start being able to see the cloud. So the water vapor is there until it condensates and becomes billions of particles together to form that cloud. You cannot see that water vapor. So it condensates, and then once those water droplets get too big for any upward vertical motion to keep that water droplet suspended, then it falls as precipitation. Now you can see it fall as precipitation hit the ground, or you can see it evaporate before it hits the ground. That's called virga. And then transpiration is the trees, the grass, where they will transpire, and then that water vapor enters the atmosphere. So during this whole water cycle, you can see transpiration from the clouds dissipating, then reforming, and then you see the snow melting off the mountains, water running down, the runoff back into the lakes, the rivers, the oceans, and then evaporation back into the atmosphere. So it's a complete cycle, so much going on at one time over the earth. So water in the atmosphere, basically in the atmosphere at every particular temperature and pressure, there's a limit to how much water vapor can exist in the air. This is called saturation. So saturation, the definition is when air cannot hold any more water vapor at a certain temperature and pressure. And what do we mean by cannot hold anymore? So one air parcel can only hold so much water. For every molecule of water which evaporates into the air, one molecule must condense out of the air. It's like a soaked sponge. If you have a sponge completely soaked, and you put one more drop in that sponge, a drop has to come out. Unsaturated versus saturated. So near the surface, water molecules both evaporating and condensing. So you have the ocean evaporating, any water puddles, the incoming solar radiation from the sun, the heat, bringing that air up, and then the water evaporating off the ground, and then reaching its condensation level. So you do have, just by the sun coming in, heating the ground, creating an updraft, just upward vertical motion, there is a level that is the convective condensation level. So at the level which clouds will form just based on heat alone. So once they reach that level, as an air partial rises, it expands and cools. Because when an air partial expands, then the molecules aren't as close together, so it actually cools. Once that cools to the dew point, or within 5 degrees of the dew point, that's when you can have saturation, and you actually create condensation, and you have the water air partial becomes saturated, and you're able to see those clouds. If you take a clear jar, fill it about 1/4 full of hot water, put the lid on it, then the vapors off of that hot water will actually condense on the inside of the jar, because the air inside of the jar is warmer than the outside. So you'll get the condensation on the inside of the jar. If you take a can of pop out of the fridge and you put it out in the sun, you'll get the condensation on the outside because it's colder inside than it is out. So this is just reversing that effect where you get the condensation inside the jar. Now if you shake the jar, then you take the condensation, it washes it off and then goes back into the water. So take a match, and took a match, light it, blow it out, and you have the smoke coming off of the match. Very quickly throw it in that jar and get that smoke into the jar and put the cap on it. Now when this condensates, it will actually condensate onto the smoke. But you have to have one other thing to actually create a cloud, is the pressure. So if you use, I keep saying a jar, but use a clear 2-liter bottle. So take a clear 2-liter bottle, fill it about 1/4 full of hot water, light a match, blow it out, throw the match into that water, and get the smoke into the bottle. So if you leave it sit, you can watch the condensation form on the inside of the bottle. Shake it, you get all the condensation off the inside of the bottle back into with the water, and then with the smoke in there, you can actually squeeze the bottle. The bottle clears up. Let go of the bottle, it's got lower pressure, and then you will see the vapor. Actually, with the smoke, you will actually form a cloud inside of that bottle. So lower pressure will allow that moisture to condensate on the smoke and actually create it's a whole cloud right above the water. If you squeeze it and create that higher pressure, then you're pushing the moisture out of the air and back into the water that's at the surface, and then it actually clear that bottle out. Then when you let go, then the lower pressure allows that water vapor to come back up and it condensate back to the smoke again. It's a pretty cool experiment if you understand what I'm talking about. So you have to have 3 things for a cloud to form. You got to have water vapor, you got to have pressure, and you have to have condensation, cloud condensation nuclei. You have to have something for that water vapor to condense to. I kind of jumped off subject there, running it back. With saturation. So can water vapor in the air condense onto a liquid out of the surface to condense on? So I jumped ahead of myself there on the last slide. So no, you have to have something to condense to. That's why if you put the hot water into the bottle and you didn't put the smoke in that bottle, then the condensation happens on the surface of that glass or on the surface of that plastic bottle. So it has to have something to condense to. That's why you take the match, you have to blow the match out, put the smoke in the air, and then you can have that moisture condense onto that smoke. So salt, soot, dust, smoke, there's some examples. What is in the atmosphere for these clouds to condense to? So every cloud in the air is condensed to dirt, salt, soot. There's something in the air that is condensed to. So if you get into the dirty air, the dirty water, the dirty air, then you're looking at more cloud cover. So if the air was actually perfectly clean, we wouldn't have any clouds. If you filtered out the air completely, we wouldn't have any clouds, wouldn't have any precipitation, no rain, and it would actually be a pretty dangerous situation. So the surfaces are called cloud condensation nuclei, or CCN. CCN must be moving slow for it to be more likely for the water vapor to condense on. So if you have a windy condition, the condensation nuclei is blowing around, then it actually changes the physics of that atmosphere, so the water vapor cannot have the time to condense on that. It just bounces off. Okay. Still in saturation, so water molecules moving at slow speeds are more likely to condense on the CCN. Air molecules, or any other molecules, move faster when heated and slower when cooled. So we talked about this in, I think, the temperature video. The molecular activity comes to a complete stop at 0 degree Kelvin. So all molecular activity comes to a stop. So when the colder it gets, the slower those molecules are moving. Faster they're moving, the warmer it is. So the important points of this, condensation is more likely in cool air, like at night. You ever see dew during the day? No. So warm air has a greater capacity of water vapor. So when a cloud forms, say an air partial rises, cools, condenses, well, that's when the air partial rises, it evaporates, cools the air to the dew point, and then that becomes saturated, and then that condenses onto that particle, that CCN. So warmer air can hold more water vapor. So when it's actually harder to get a cloud out of warmer air. I know it seems kind of opposite, but you have to have more moisture to get a cloud out of warmer air than you do colder air. But in the warmer air, that's why we have the heavier rains, the more consistent rainfalls, either showers or just steady rain in a stable environment. Humidity expresses how much water vapor is in the air. Lots of ways to express humidity. Most common way is relative humidity, and we'll cover that here in a few minutes. And first, you have vapor pressure, the portion of the total vapor pressure due to the pressure exerted by water vapor alone. So if you took an air partial, just a ball of air, and you extracted all the water vapor out of that air, put it on a scale, how much does it weigh? That's your vapor pressure. High vapor pressure equals a lot of water vapor in the air. Low vapor pressure is little water in the air. So you're just taking the vapor pressure, just that vapor, water vapor, out of the air and measuring how much it weighs. So vapor pressure, example, is if the surface pressure was 1,000 millibars, 78% was nitrogen, that would be 780 millibars. 21% of that's oxygen, that's 210 millibars, and 1% water vapor, that's 10 millibars. Then your water vapor pressure is 10 millibars. All right, saturation vapor pressure. For any temperature and pressure, there's a maximum number of water vapor molecules that the air can hold. Like I said before, with saturation, it's only so much water it can hold. You put a drop in, a drop has to come out. So saturation vapor pressure is the pressure that molecules would exert if the air were saturated. So if the air is completely saturated, how much pressure would that completely saturated air partial exert on the surface? That is your saturation vapor pressure. So your vapor pressure is if you took the water vapor out of the air and you measured the weight, that's your vapor pressure. If you saturate it, completely saturated, soaked, and you took that and weighed it, then that's your saturation vapor pressure. So since warm air has a greater capacity for water vapor, it takes much more water vapor to saturate the warm air. We spoke about that earlier. This means warm air has a higher saturation vapor pressure. All right, humidity specifies the amount of water vapor in a volume of air. So like we keep talking about an air parcel, just an air parcel can be any size. Just take an example of a basketball. There's our air parcel. How much water vapor is in that air? If you shot moisture into that air of that basketball, then how much moisture is in that air parcel? And then you take your percentages and that's how you figure out your humidity. So in meteorology, we use the term air parcel. It's described as a particular volume of air. So whatever volume of air you want to use for that air parcel. And there's 4 ways to express humidity. Like we talked about earlier, relative humidity is the most common. So absolute humidity, the weight of the water vapor per volume of air. So what's the weight if I took a basketball full of air and I extracted the water vapor, how much does that weigh? That's the absolute humidity. Or how much weight of water vapor per that volume of air, that percentage is your humidity, absolute humidity. Specific humidity is the weight of the water vapor per the weight of all the air in the parcel. So if you weighed the water vapor and you weighed all of the air in the basketball, then that percentage, the difference there is your specific humidity. The mixing ratio is the weight of the water vapor, the weight of the dry air in the parcel. So you separate the two. You separate the water vapor, and then you separate the dry air, and then that percentage would be the mixing ratio. And then relative humidity, that's what we use, the water vapor content per water vapor capacity. So it's water vapor content versus how much water vapor that air parcel can hold. And then water vapor per saturation vapor pressure. So how much water vapor is in the air versus per how much of it's actually saturated. So if you take that ratio, then you have actually how much moisture is in the air as a whole. That percentage is your relative humidity. All right, relative humidity, like I said, is the most commonly used. It can be misleading since it doesn't actually indicate how much water vapor is in the air. It's given in percentage, so 50% of humidity means that half of the air is saturated. But does 50% humidity in the warm air indicate the same amount for water vapor, 50% relative humidity in cool air? No, since the warm air has a greater capacity for water vapor. It takes more water vapor to become half saturated. So if you have an air parcel like a basketball and you say we want to go 50% saturated, we're going to have to add a lot more water than we would if it was cold air to become saturated. Because you think of it like the temperature is a lot higher than the dew point. Once you got to cool that temperature down to the dew point to become saturated. So with warm air, it takes a whole lot more water to bring that air temperature down, to cool it. Evaporative cooling, bring that down to become saturated. Cold air, the temperature is already there, so now you only have a few degrees you have to cool that air parcel off of to get into that saturation level. So anything that's a 5% or 5 degree dew point depression, which is 5 degrees difference between the dew point and the temperature, that is where you have saturation. All right, humidity. 2 ways to change relative humidity. You can add more water vapor to the air. So if your temperature is 90 degrees and your dew point's 50, you have to add more water vapor to cool that air to bring that temperature down closer to 50 So you add more water vapor. So the water vapor will cool the air. Change the air's temperature. That's essentially what you're doing with the water vapor. You add the water vapor to bring that vapor up, or cool the temperature. When the sun goes down, the temperature starts to cool, come down closer to the dew point. That's why you wake up in the morning and there's fog. All right, if the temperature stays the same, adding water increases relative humidity. So if you add that water vapor, you don't have to bring the temperature down. You just add the water vapor to bring the percentage of moisture in the air up, and that's a higher relative humidity. Removing water decreases relative humidity, dries it out. So if it rains, typically what you get, like in the summertime, if it rains, then it's like, I hate those rain showers where they're, rains for 15-20 minutes and it's a hot day. It's like it feels good for 15-20 minutes, and then all of a sudden it gets so humid out because of the evaporation, and then it actually feels worse afterwards. So if the water content stays the same, increasing the temperature decreases relative humidity. So if you don't add any more moisture to the air partial, and you increase that temperature, now you'll need more water vapor to bring the relative humidity up. So if you increase that temperature without adding more moisture, then your relative humidity does decrease. And decreasing temperature increases relative humidity. So if you decrease the temperature closer to the dew point, then you become more saturated. That becomes a higher relative humidity. And basically, here's a graph. As the humidity increases, the temperature decreases, the humidity increases. As the temperature increases, the humidity decreases. So they are basically inversely proportional. When you think about temperature increase, it gets further from the dew point, drier air. Temperature decreases, get closer to the dew point, more saturated air. All right, dew point temperature. The temperature in which air would have to be cooled for saturation to occur. So we've talked about that over and over. Cool the temperature to the dew point, becomes saturation. That's the cloud formation. Okay, get the air partial up, bring the water vapor up with the air partial, and then if the water vapor is already present in the air, you bring an air partial up, cool it to the dew point. It expands, cools, then condensation happens on the CCN, and then a cloud forms. High dew points equals high water vapor content. So the higher the dew point, the closer you are to the temperatures, the higher the moisture content in the atmosphere. Low dew points, low water vapor content, and adding water increases the dew point. At what temperature does that air partial have to reach to become saturated? For saturation to occur. So if you add more water, then that increases the dew points. It brings it closer to your temperature. If you decrease your temperature, that becomes a higher relative humidity and becomes saturated faster. All right, moving water from the air decreases dew points. So if you've got a drier air, then you're going to have to, that's going to bring your dew point way down. Now you're going to have to either cool that temperature even further, or put the water back. The closer the actual temperature is to the dew point temperature, the more humid it is, or the more humid it feels. So typically, relative humidity is how humid it is. When does it become uncomfortable? That's kind of the thing. The only reason we use humidity is, not the only reason, but one of the main reasons is what's humidity? Is it going to be 80% a day, 60% a day? About 60%, starts getting up above 60%. That's where, it starts to feel uncomfortable. That's the main thing people look at. Oh man, it's going to be humid today. So if you hit, 60, 70% humidity, then it's just going to be an uncomfortable day. you're going to feel a lot warmer, muggy, harder to breathe than it normally is. Dew point temperature can never be higher than the actual temperature. So, like I said, when you bring that temperature down to the dew point, that is as far as you can go. Then it's 100% saturated. You can never raise that dew point above the temperature or drop the temperature below the dew point. That's the dew point is simply what temperature does an air partial have to reach to become saturated. That's it. There's no variance on being higher than the temperature. With the temperature being lower than the dew point, it just can't happen. And it can be equal, and when it is equal, that's 100% humidity. All right, dew point temperature. Dew point is actually a better indicator of how much water vapor is in the air than relative humidity. Like I said, the relative humidity, we covered that. It's 4 ways to determine humidity, and that's, doing how much moisture is in the air versus dry air versus moist air versus what's total air. So the dew point is actually the better indication. So relative humidity tells us how close the air is to being saturated. 100% humidity means the air is saturated, very humid. It does not mean that there's a lot of water vapor in the air. And depends on temperature. If relative humidity is 100% and the air temperature is 75 degrees, there's a lot of water. If relative humidity is 100% and the air temp is 10 degrees, no, because it's dry, because the cold air cannot hold as much water vapor. So you can still have 100% humidity, even though it's 10 degrees outside. It doesn't feel like it's muggy. And the dew point is an actual number. So 70 degrees or 72 degrees. That dew point is an actual number. That's the temperature at which that air partial has to reach to become saturated. So it's a more accurate way to get your humidity. Humidity and the human comfort or discomfort. And we talked about this. How does the body cool itself? Like exercising, we sweat. Evaporation. So evaporation is a cooling process. We covered that in first or second video, I believe second video on that. So as we sweat, our sweat evaporates and cools us down. So that happens very easily in dry air. When it's dry out, that can hold plenty of moisture, so it evaporates right into the air. Dry air has a lot of room for water vapor, as we just said. But what about when the air has a lot of water vapor in it? So now what happens? Not as much evaporation, or it's really it's not as much evaporation. It's a slower process of evaporation too. Happens when relative humidity is high or the dew point is high. The wet bulb temperature, the lowest temperature that can be reached by evaporating water into the air. So when you evaporate water into the air, it cools the air, and that whatever the lowest temperatures that can be reached during that process, how much water vapor is in the air, or how much water is available to evaporate into the air to cool that, what temperature would that reach? If you evaporated all the water that was on the ground up into the air, what temperature would that reach? That gives you your wet bulb. If the wet bulb temperature is low, lots of evaporation, cooling can occur. If high, not much evaporation or cooling can occur. So when you have a high wet bulb temperature, if you're exercising, when you start to sweat to cool yourself, not a lot of evaporation is taking place, so you can actually overheat. So the military uses this for the wet bulb temperature, actually for their to determine, it's in an equation to determine their red flag, green flag, yellow flag, red flag, black flag. If it's a black flag condition, then you shouldn't be exercising at all. The closer the wet bulb temperature is to the actual temperature, the more humid it feels. And the heat index, and apparent temperature due to temperature and moisture. Alright, here's an index chart. Alright, measuring humidity with a psychrometer. If you see that little sock on the lower hanging thermometer, I use one of these in the military. It's a sling psychrometer, and you actually wet that sock, and then that gives you your temperature and your wet bulb. And then we input that, and we determined what the heat index was to tell the Marines if it was safe to exercise or not. Measuring humidity with a hair hygrometer. Never seen one of these. Pretty cool picture. You take human hairs, expose them to the atmosphere, put some tension on them, and then you can zero your gauge, or calibrate your gauge based on whatever humidity. And then as the humidity increases, the needle will move because hair expands and it actually changes during humidity. I guess if you had a bad hair day, then you would know your hair actually gets thicker and less manageable in humid conditions. So it's like women get out of the shower, they tend to blow dry their hair right away, just because if they leave it, they know it's just going to be a mess and it's going to stay that way when it does dry. So condensation near the ground. Recall that air near the ground cools off quickest on calm, clear nights by conduction. So if from a previous video, air sits on the ground, no incoming solar radiation, it's nighttime, the earth is emitting that radiation, or it's cooler on the ground, the air sits on the ground, and on that cold ground, then the air actually gets colder at that surface. So same thing with the heat by conduction. When the air mass moves over a hotter land, it actually warms the bottom of that air mass. Same thing with cooling. So if overnight air moves through over the colder ground, then it cools to the dew point, and then you actually can create an inversion where temperature increases with height because it's colder on the surface. Then it caps it and actually will hold that moisture to the surface, and you'll get that radiation fog. You get fog at the surface. Air reaches its dew point the quickest right there at the surface, right on the ground. Water starts to condense out of the air onto surfaces, cars, grass, trees, etc. And form of the condensation depends on the temperature. So if it's fog, freezing fog, ice particles, you can have freezing fog in the air. You can have fog, that water particles that actually super cooled at the surface, and then they hit a surface and create ice on that surface as they impact. Dew, condensation in liquid form, forms on nights when temperatures is greater than 32 degrees above freezing. Most likely on calm, no mixing, clear, maximum cooling nights. So calm winds, if you get too much of a wind and you get way too much mixing, you can't get that condensation because the air just blows and it just dries everything out. So it has to happen on a calm night, calm winds, and a clear night to get the maximum cooling. Alright, the frozen dew is ice form of dew. So dew forms on a surface, temperature drops, and then the dew freezes. That is frozen dew. So is it frost? The same thing? No. That happens, the frozen dew happens when condensation occurs while temperature is above freezing then the temperature drops below freezing, and then that dew freezes. That is the frozen dew. So frost is frozen from the start. And so the water vapor in the air just freezes, changes state straight to a solid onto a surface. That's the frost that you get. That's why it's more of a like a rime ice. It's more aerated or white in color. And it occurs when the air becomes saturated at temperatures below 32 degrees. So if there is water vapor in the air, it's already below freezing, temperature drops to the dew point, saturation happens, and it's just frozen right out of midair. That's a deposition. Alright, still in condensation near the ground. Haze. Condensation on suspended particles. So you get haze. The difference between haze and fog is actually how far you can see. So fog technically is less than 5/8 of a mile. If you can't see 5/8 of a mile, then it's considered fog. If you can see more than 5/8 of a mile, then it's considered haze or mist. Haze, condensation on suspended particles. Well, clouds is condensation on suspended particles. So it forms when relative humidity is high enough to allow some water vapor to condense on small floating particles, hygroscopic water seeking. Like relative humidity goes up, droplets increase in size. When visibility drops below 1 kilometer, 0.62 miles, it is no longer haze. Fog, basically a near ground cloud. And it forms in two ways. And we'll cover fog formation, cooling of the air to saturation. So if the air cools down to the dew point, becomes saturated, the fog can form if the water vapor is in the air to allow fog to form. Evaporation of water into the air. So if you evaporate water into the air, it actually cools the air, brings temperature to the dew point, becomes saturated, and becomes fog. Just like clouds, fog droplets see condensation nuclei on which to form. So there has to be some sort of dust in the air, dirt, dust, smoke, soot. Something has to be in there for it to condensate too. And there are four main types of fog: radiation fog, advection fog, upslope fog, and evaporation fog. And I believe this is the end of our show here. We'll cover the fogs, we'll cover clouds a little bit more, I think, in the next video. We do have a whole nother video I'm preparing now for fog formation. Give me another week or so to get that out.